Conroy, and my senior project was creating dye-sensitized solar cells. So my central question for this project was, what are the steps necessary to create dye-sensitized solar cells that can act as a power source? So why did I choose this project? Last June 2021, I had the opportunity to attend a biotechnology program through the National Student Leadership Conference in Washington, D.C. At this program, we did an activity where we built dye-sensitized solar cells. I found this activity to be fascinating, and I really wanted to take it a step further, and it fit within the requirements of both my STEAM capstone project and the senior project. This also relates to sustainability and engineering, two topics that greatly interest me and what I hope to do in the future. And it would allow me to implement the engineering design process outside of structured classroom projects and kind of see those steps in action in a more independent way. So now I'm going to explain how dye-sensitized solar cells work. I have a couple examples right here of the ones that I made. So there are 5 main components, which I'll each talk about more in detail in the next few slides. The 5 components are conductive glass, titanium dioxide, photosensitive dye, a counterelectrode, and electrolyte solution. So first, the conductive glass. It's just these 2 pieces of glass here that kind of make up the majority of the solar cell. What these do is it allows light to pass through into the cell, and it provides a surface for the titanium dioxide and dye to sit on, as well as the pencil graphite, which is the counterelectrode. The specific kind of glass I was using is indium tin oxide, or ITO, conductive glass, and this just means there's a thin layer of the ITO on one side of the glass that gives that part of the glass a slight electrical charge. So the titanium dioxide and photosensitive dye combine to form what's called the anode. It's kind of like the positive side of a battery. And so what the titanium dioxide does, it's this like white substance that you can see here. It acts as a sponge for the dye. The specific kind of dye I was using is just blackberry juice dye, and it allows UV light to be absorbed into the cell, kind of how a plant would absorb light from the sun with photosynthesis. Then the counterelectrode, which is called the cathode, it's kind of like the negative side of the battery. It acts opposite that anode. And what it does is it breaks down the electrolyte solution into usable components and allows the cell to function. I specifically was using pencil graphite. That was super easy to find in a classroom setting, and it was very cheap and accessible for me to use. And then lastly, the electrolyte solution. This is probably the most important component of the cell. It adds electrons into the solar cell, which flow throughout the cell to generate power when hit with that light energy, and then it's broken down by the cathode and flows through the cell kind of in a cycle. So here's kind of a diagram of what the solar cell looks like. This purple side is the titanium dioxide and the blackberry juice. This white side is the cathode, the pencil graphite. So what happens is I would take electrolyte solution in a pipette, drop it into the solar cell, and once that electrolyte solution flows throughout the cell, it moves towards the titanium dioxide and the blackberry juice. Light comes in through that side of the cell, is absorbed by the blackberry juice, and gets those electrons of the electrolyte solution moving super fast and flowing around. Then they start to kind of cycle through back towards the cathode, the pencil graphite, and are kind of broken down, start moving slower again, kind of go back to their normal state. And this continues until the electrolyte solution has been exhausted and those electrons are used up. Then the cell kind of isn't quite functioning so anymore, and you can add more solution to keep it going. And so what happens is, to generate power and get an actual power reading, those electrons just keep cycling throughout the cell, and you can use it to power something like this motor that I have here. So to actually go about building my solar cells and using them as a power source, I started out by creating a procedure to create my solar cells. To do this, I used a couple of tutorials, specifically the tutorial I used at that biotechnology program, and another one, and kind of pieced them together based on the materials and facilities that I had access to. I then wrote a procedure to wire all of my solar cells together and actually attach them. And here's a picture of the fan that I had intended to power my solar cells with. I started out by taking it apart and looking at all the circuitry to figure out where I actually was going to attach my solar cells and how I was going to remove the solar panel that previously had been powering it. So then I kind of moved into like the building phase. I started building all of my solar cells, which you can see here. So I first started by creating the titanium dioxide paste. This was just combining titanium dioxide powder and vinegar. I then spread the paste in wells, and I just made the Scotch tape on the conductive side of one of these pieces of glass. I spread it throughout the well with a stirring rod which you can see in that image there, and then annealed them on a hot plate, which basically just melts the titanium together and makes it strong enough to function in the cell. Once that was done, I added blackberry juice, which I just went to Roach Brothers, bought blackberries, and mashed them up in a beaker, and then just put the blackberry juice onto the titanium dioxide, which is this third image here, and then rinse with water to remove the excess juice, and then isopropyl alcohol to dry them out. And in the end, they looked like this image here. It's a little hard to see, but they're just a big square of like purple on one side of the glass. Then to create the cathode, I took the other half of the glass pieces that I had and just took a pencil and colored over that conductive side. I then used binder clips to attach the end of the cathode, kind of like a sandwich, leaving the top and bottom sides a little bit uneven. It's kind of hard to see here, but these two are off center, and then these sides are even with the binder clip. Once that was done, then I had all of my solar cells ready. I added electrolyte solution to the top with a pipette and just used the binder clips to kind of unclip and unclip them and let it flow throughout the cell. So once that was done, all of my solar cells were ready and functioning, I used the multimeter to figure out the power output that I had in total with all 9 of my solar cells. To do this, I just attached wires and alligator clips to the multimeter and my solar cell, as you can see here. And I calculated the total voltage I had for all of them was about 57 watts. This wasn't enough to power the fan that I originally planned on working with, but should have been enough to power this small motor that I have up here that's attached to the fan. This I calculated on March 3rd, which is when I finished building all of my solar cells. I started working on them over February break, and then finished them up on that half day. After that, I planned on wiring all of my solar cells together in series, which is just wiring them together in a big line so the power kind of moves down it like a conveyor belt into the motor at the end. But when I went back to work, my next work opportunity was the half day on April 6th, but by that time, the components of my solar cells had degraded, and so they weren't able to generate power, so I wasn't actually able to complete this phase, but I did have the procedure all written out of what I was going to do. So here are some pictures of the degraded solar cells. I also have them here. You can tell they're definitely like much more of a white color. They're no longer the nice purple that they were, which indicated to me that the blackberry juice had broken down over time and no longer was able to absorb light properly so that the cell could function. This kind of brought my project to a halt, and so I was unable to continue and finish completely how I had intended to. So looking back, what went well with this project? I was able to create 9 working solar cells. I have 2 of them here with me. And I was able to develop and write a procedure to create both my solar cells and wire everything together. I also was able to learn about another alternative energy source that I hadn't ever heard about before. And I was able to do this in a hands-on way by actually creating it myself and learning and being able to see at the same time how all of those components work. I also was able to practice the engineering design process in an independent way like I had hoped to, and kind of see how all of those steps work and kind of work it out myself. So what could have gone better? Definitely having less time between work sessions. This definitely would have made my solar cells be able to actually function as a power source, and would have allowed for the blackberry juice to continue functioning. I also definitely could have used my time more efficiently during the summer. For STEAM, we had to have our project ideas finalized at the beginning of last summer, so I knew I was going to do this project in July of 2021. I definitely should have taken that time during the summer to order materials and get my background research and procedures written, so that way coming into the school year, I would have had more time to go back and revise based on things that didn't quite go so well and the different problems that arose throughout the year. And so if I had more time to do this project, I definitely would go back and rebuild all of my solar cells, because the procedure that I wrote did work. I did have solar cells that generated power, just the timing of everything didn't quite work out. I also definitely would try to work over the span of a few days instead of over multiple months, hopefully making use of like a school break or something like that to work, instead of trying to work on half days that were super spread out. Also, I definitely would want to apply for grants and look at different ways of funding to help alleviate some of the costs of this project, and also look to develop some type of STEAM workspace in the school. I was lucky enough to have Ms. Gopis as my mentor, who let me use her classroom, come in over break, and would was willing to stay with me after school and all of that kind of stuff to help supervise me while I work and allow me to use her classroom. But it definitely would be helpful to have somewhere in the school for other STEAM scholars and anyone who wants to do some type of STEM-related project to be able to have a designated mentor or just designated space so that they can work on their own schedule. So that is it. Thank you for listening. Does anyone have any questions?